So here the hypotenuse AC equals to C units in its length according to our definition. But the hypotenuse AC from Domit is very easy to see that AC, the hypotenuse AC equals to AS plus SC. Again, the hypotenuse AC equals to AS plus SC. Okay. So the hypotenuse AC that is equal to C, in total it is equal to AS plus SC. So you can write here that C equals to AS is A minus X, plus SC is B minus X. So in total, C equals to A minus X plus B minus X. That is to say, C equals to A plus B minus X is minus 2X. Okay, so therefore the hypotenuse C is equals to A plus B minus 2X. Here we will add 2X to this equation, and we get that 2X plus C equals to A plus B. We subtract C from this equation and we get that 2X equals to A plus B minus C. We divide this equation by 2 and finally we get that X equals to A plus B minus C over 2. So actually we succeeded to find a general formula for the radius of a circle that is blocked by a right triangle. The radius x of this circle that is blocked by the right triangle, triangle ABC, must be equal to A plus B minus the length of the hypotenuse that is C over 2. Again, the radius of this circle that is equal to x according to our definition must be equal to A plus B minus C over 2. Now we'll use this formula in order to find out the radius of this circle that is blocked by the radius of this circle that is blocked by the right triangle, triangle ABC. And we'll get that we define the radius of this circle as R, so the radius R of this circle that is blocked by the right triangle, triangle ABC, according to the new formula, will be equal to AB plus BC minus AC over 2. Repeat again. The radius of this circle is equal to R, according to the new formula, will be equal to AB plus BC minus AC over 2. So the radius R equals to AB. AB is 7, therefore we substitute AB by 7, plus BC. BC is 24, we substitute BC by 24, minus AC. AC is 25 over 2. So in conclusion, found that the radius of this circle that is equal to R according to our definition must be equal to 7 plus 24 is 31 minus 25 over 2. 31 minus 25 is 6, and 6 over 2 is 3. So I found out in conclusion that the radius of this circle that is blocked by the right triangle ABC, the radius R equals to 3 units. Likewise, we calculate the radius of this circle that is blocked by the right triangle ADC. We define the radius of this circle as x. According to the new formula, the radius of this circle x that is blocked by the right triangle CDA must be equal to CD plus BA minus CA over 2. Repeat again. According to the new formula, the radius of this circle that is equal to x according to our definition must be equal to CD plus DA minus CA over 2. CD is 7 plus DA is 24 minus CA that is 25 over 2. So 7 plus 24 is 31. 31 minus 25 over 2. 31 minus 25 is 6, and 6 over 2 is 3. So finally we found out that x equals to 3 units. So the radius of this circle that is blocked by the right triangle CDA, it is also equals to 3 units in its length. In the next step, we will define the point of tendency of tangent BC with this circle as point M. So PM is the radius of this circle that is equal to 3 units. The radius PM is drawn to point M, that is the point of tendency of tangent BC with this circle. Whenever our radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MP. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Likewise, we define the point of tendency of tangent AB with this circle as point N. We join points P and N together by straight line. Pn is the radius of this circle that is equal to 3 units. The radius Pn is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever our radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. So inside quadrangle NPBN, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of this fourth angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, the missing angle must be equal to 90 degrees. I'll repeat again, in order to complete the sum of the angles in this quadrangle NPBM to 360 degrees, the missing angle here must be equal to 90 degrees. So inside quadrangle NPBM, we have 4 right angles. Therefore, we can relate to this quadrangle NPBM is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, side NP equals to the opposite side BM in rectangle NPBM. But NP equals to 3 units, therefore BM must be also equal to 3 units in its length. Likewise, according to the sum that the opposite sides of rectangle are equal to each other, we get that PM equals to NB. But PM is 3, therefore NB must be also equal to 3 units in its length. So actually found out that quadrangle NPBM is not a rectangle but a square. Why? Because all of its sides are equal to each other. Each side of this square NB equals to 3 units. If we repeat on the same process here, we get that here we have also square. We define the point of tendency of tangent dA with this circle as G. According to rule number 1, QG is the radius of this circle that is known to point G, that is the point of tendency of tangent AD with this circle, and therefore tangent dA will be perpendicular to the radius GQ. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. We define the point of tendency of tangent DC with this circle as K. We join point Q and K together by straight line. QK is the radius of this circle that is equal to 3 units. The radius QK is drawn to point K, that is the point of tendency of tangent DC with this circle, and therefore tangent DC will be perpendicular to the radius KC, to the radius KQ. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. So inside quadrangle KQGD we have 1, 2, 3 angles, therefore the fourth angle must be equal to 90 degrees. Therefore, we can relate to quadrangle KQGD as a rectangle. We know that the opposite sides of the rectangle are equal to each other. That is to say, KQ equals to DG. But KQ is 3, therefore DG must be also equal to 3. According to the same rule, in rectangle KQGD, side QG must be equal to side KD. But QG is 3, therefore KD must be also equal to 3 units. So we found out that quadrangle KQGD is not a rectangle but a square. Those two squares are identical to each other because each side of this square is equal to 3 units. Okay. In the next step, we will extend the radius GQ of this circle by straight line until it touches side BC of the rectangle ABCD. We define the touching point of the extended radius GQ with this circle as point T. So in quadrangle TCDG, in this big quadrangle TCDG, we have 1, 2, 3 rectangles. Again, in this quadrangle TCDG, we have 1, 2, 3 rectangles. Therefore, the fourth angle must be equal to 90 degrees. According to the rule, that the sum of the angles in any quadrangle is equal to 360 degrees. This angle must be equal to 90 degrees. Therefore, inside quadrangle GDCT we have 4 right angles. Therefore, we relate to this quadrangle GDCT as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side DG equals to side TC. But DG is 3, therefore TC must be also equal to 3 units in its length. According to the sum rule, in rectangle GDCT, side DC must be equal to side GT. But DC is 7, therefore GT must be equal to 7 units in its length. So we can write here that GT equals to 7 units in its length. In the next step, we will extend the radius NP of this circle that is equal to 3 units by a straight line until it touches side DC of this rectangle. And we define the touching point of the extended radius NP inside DC is point L. So we created here quadrilateral NBCL. In this quadrilateral NBCL, we have 1, 2, 3 right angles. Therefore, the fourth angle must be equal to 90 degrees. So this angle equals to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral NBLC we have 4 right angles. Actually inside quadrilateral NBLC we have 1, 2, 3, 4 right angles. Therefore, can relate to this quadrilateral NBLC is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side NB must be equal to the opposite side LC. But NB is 3, therefore LC must be also equal to 3 units in its length. Likewise, according to the sum rule, in rectangle LNBC, side BC must be equal to side LN. But BC is 24, therefore NL must be also equal to 24. Here we can write down that NL equals to 24 units in its length. And we already found out that GT equals to 7 units in its length. We define the intersection point here as Z. Inside this small quadrilateral ZLTC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be equal to 90 degrees. So inside the small quadrilateral ZLTC, we have 1, 2, 3, 4 right angles. Therefore, we can relate to this small quadrilateral ZLTC as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, this rectangle ZLTC, TC must be equal to ZL, but TC is 3, therefore ZL must be also equal to 3 units. In the same rectangle ZLCT, LC must be equal to ZT, but LC is 3, therefore ZT must be also equal to 3 units in its length. Okay, so here we extended the radius GQ by a straight line until it touches side BC at point T. When you extend a straight line by a straight line, the result is a straight line. So GT in total is one straight line. But GT equals to 7 units. So GT is 7 minus GQ that is 3 minus ZT that is also 3 must be equal to the missing side QZ. So QZ equals to GT that is 7 minus GQ that is 3 minus ZT that is also 3. So write it down. QZ, the length of this line segment QZ in total must be equal to GT, that is 7, minus GQ, that is 3, minus ZT, that is also 3. Repeat again, the length of this line segment QZ must be equal to GT, that is 7, minus GQ, that is 3, minus ZT, that is also 3. So 7 minus 3 is 1. So in conclusion, we know that QZ equals to 1 unit in its length. QZ equals to 1 unit in its length. We have already found out that NL equals to 24 units. We extended the radius NP by straight line, therefore the result the result is NL. When you extend the straight line by straight line, the result must be a straight line. So NL is one straight line, and it is equal to 24 units. So NL, that is 24 minus NP, that is 3, minus ZL, that is also 3. Again, NP, that is 24, minus NP, that is 3, minus ZL, that is also 3, must be equal to the missing side PZ. Okay? So PZ equals to NL, that is 24, minus NP, that is 3, minus ZL, that is 3. So PZ in total equals to 24 minus 3 is 24 minus 6, that is 18. So if I found out that the length of this line segment PZ, it is equals to 18 units in its length. Okay. We extended the radius GT by straight line. We extended the radius GQ of this circuit that is equal to 4 units by straight line, and the result is GT. When you extend a straight line by straight line, the result must be a straight line. So GT is one straight line. If you focus on this side of the straight line GT at point Q, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of the straight line GT at point Q? We have this angle that is equal to 90 degrees, plus the missing angle. In total they must be equal to 180 degrees according to the rule that I mentioned. Therefore the missing angle here must be equal to 90 degrees. If you focus on this side of the straight line DC is one side of rectangle ABCD, therefore it is absolutely a straight line. If you focus, so this angle equals to 90 degrees according to rule number 1. We found out that according to rule number 2, this angle also equals to 90 degrees. So here, if we focus on this side of the straight line DC at point N, the sum of the angles on this side of DC at point N must be equal to 180 degrees. So which angles we have at this side of DL at point N? We have this angle that is equal to 90 degrees, plus the missing angle. In total they must be equal to 180 degrees according to the rule that I mentioned. Therefore the missing angle must be equal to 90 degrees. So inside quadrangle Q, K, L, Z, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. So this angle equals to 90 degrees. Then we focus on the straight line NL. NL is one side of rectangle NBCL, therefore it is absolutely a straight line. And L is a straight line that is equal to 24 units. So if we focus on the upper side of the straight line NL at point Z, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of NL at point Z? We have this angle that is equal to 90 degrees, plus the missing angle. In total they must be equal to 180 degrees. Therefore the missing angle here must be equal to 90 degrees. So actually found out that triangle QPZ is a right triangle. So in the next step we'll implement the Pythagoras theorem on the right green triangle, triangle QZP. Repeat again, we'll implement the Pythagoras theorem on this right green triangle, triangle QPZ. So So I copy triangle QPZ in a new page and we will implement on it the Pythagoras theorem. So actually, this is the right triangle QPZ that they copied from the original drawing. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in this right triangle QPZ, we'll get that QP square, that is the line segment that we are looking for, must be equal to QZ square plus PZ square. So QP square, that is the square of the hypotenuse, must be equal to QZ square. QZ is 1, therefore QZ is 1 square, that is 1, plus PZ square. PZ is 18, therefore PZ square is 18 square, that is 324. So QP square, that is the square of the hypotenuse, equals to 324 plus 1 is 325. Here we take a root out of this equation and we get that QP equals to the square root of 325. But 325 is 25 times 13. Here we take 25 out of the root. The square root of 25 is 5. So inside the root we left only with 13. In conclusion, we found out that the distance between the centers of those two circles, that is to say the length of this line segment QP, equals to either 5 times square root of 13 units, or in terms of numbers, QP equals to 18.03 units. So repeat again, the answer to this question is that the distance QP between the centers of those two circles, equals to either 5 times square root of 13 units, or in terms of numbers, QP equals to 18.03 units. So a little bit more than 18 units. And that is the answer to our question. In the next step, I'll summarize the lecture. So, in this lecture, we found out the distance between the centers of those two circles, that is to say, the length of this line segment QP. Again, point Q is the center of this circle, and point P is the center of this circle. And we have to find out the distance QP, that is the distance between the centers of those two circles. In the drawing, we have rectangle ABCD. Side AB of this rectangle equals to 7 units in length. Side BC equals to 24 units in length. Inside this rectangle ABCD, we have those two circles. And our mission is to find out the distance between the centers of those two circles, that is to say, the length of this line segment QP. So first of all, because of the fact that ABCD, this is a rectangle, we know that all those 4 angles are right angles, because all the angles inside the rectangle are right angles, so those 4 angles are all right angles. And we also know that the opposite sides of rectangle are equal to each other, that is to say, side AB equals to side DC, but AB is 7, therefore DC must be equal to 7 units in length. According to the same rule, In rectangle ABCD, side AD must be equal to side BC, but BC is 24, therefore AD must be also equal to 24 units in its length. So here we focused on the right triangle, triangle ABC, and we implemented the Pythagoras theorem on the right triangle ABC. According to the Pythagoras theorem on this right triangle, triangle ABC, we'll get that AC squared equals to AB squared plus BC squared. Repeat again. In the right triangle, triangle ABC, AC squared equals to AB squared plus BC squared. So AC squared, that is the square of the hypotenuse, equals to AB squared. AB is 7, therefore AB squared is 7 squared, that is 49, plus BC squared. BC is 24, therefore BC squared is 24 squared, that is 576. So AC squared in total equals to 49 plus 576, that is actually 625. AC squared equals to 625. We took a root out of this equation. And finally we found out that AC equals to the square root of 625, that is actually 25. So we found out that actually the length of the hypotenuse AC on the right triangle ABC, AC equals to 25 units in its length. So here we have this circle is blocked by the right triangle ABC, and this circle it is also blocked by the right triangle, triangles ADC. Therefore, in the next step we created a general formula that will help us to find out the radius of any circle that is blocked by a right triangle. So here we have this is triangle, the right triangle ABC. In this right triangle ABC we have this circle that is blocked by the right triangle. According to our definition, the radius of this circle is x. So we developed a new formula that will help us to find out the length of this radius that is x, only by knowing the side lengths of this right triangle that blocks this circle. Here we define the point of tendency of tangent BC with this circle as M. OM is the radius of this circle that is drawn to point M, that is the point of tendency of tangent BC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. We define the point of tendency of tangent AB with this circle as N. We join points O and N together by straight line. ON is the radius of this circle that is equal to X. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. So inside quadrilateral ON BM, we have 1, 2, 3 right angles. This angle equals to 90 degrees because ABC is a right triangle. So we have here 3 right angles. Therefore, the fourth angle must be equal to 90 degrees. So inside quadrilateral ON BM, we have 4 right angles. And therefore, we can relate to this quadrilateral ON BM is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, OM equals to NB, but OM is X, therefore NB must be also equal to X units in its length. Likewise, according to the same rule, ON must be equal to MB, but ON is X, therefore MB must be also equal to X. So we have found out that quadrilateral ON BM is not a rectangle but a square. Why? Because all of its sides are equal to each other. Its side here equals to X. And what is the length of this line segment AN? AN equals to AB minus NB. That is to say, AN equals to AB, that is A, minus NB, that is X. So in total, AN equals to A minus X. Likewise, we found out the length of this line segment CM. From drawing, it is very easy to see that CM equals to CB minus MB. That is to say CM equals to CB, that is B, minus MB, that is X. So in total, CM equals to B minus X. So in conclusion, we can say that CM equals to B minus X and AN equals to A minus X. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. We have the common standpoint point P. From the common standpoint point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule number 2, they are equal to each other. That is to say, PA equals to PB. So whenever you draw from a common standpoint of a circle two tangents to that circle, then the length of those two tangents must be equal to each other. In this case, PA equals to PB. We can implement rule number 2 in our drawing. In our drawing, we have the common standpoint point A. From the common standpoint point A, we have two tangents to the circle, tangent AN and tangent AS. And according to rule number 2, they are equal to each other. That is to say, AN equals to AS. But AN is A minus X, therefore AS must be also equal to A minus X. Likewise, the next step, we focus on the common standpoint point C. From the common standpoint point C, we have two tangents to the circle, tangent CS and tangent CM. And according to rule number 2, they are equal to each other. So CS equals to CM, but CM is B minus X, therefore CS must be also equal to B minus X. So the hypotenuse AC, it is equal to C units in its length, according to our definition, from one side. But from the other side, AC equals to AS plus SC. Again, C equals to AS plus SC. So C equals to AS, that is A minus X, plus SC, that is B minus X. So in total, C, the hypotenuse C equals to A minus X plus B minus X. That is to say, C equals to A plus B minus X is minus 2X. So in total, C equals to A plus B minus 2X. We added 2X to this equation and found out that 2X plus C equals to A plus B. We subtracted C from this equation and found out that 2X equals to A plus B minus C. We divided this equation by 2 and finally found out that X equals to A plus B minus C over 2. Okay, so here we found out a general formula for the radius of a circle that is blocked by a right triangle. So that one can find out the value of X only by knowing the side lengths of the right triangle ABC that blocks this circle. That is to say, the radius X must be equal to A plus B minus C over 2. So it is actually the sum of the lengths of the perpendiculars of the right triangle ABC, that is A plus B, minus the length of the hypotenuse, that is C, over 2. So the radius of this circle X equals to A plus B minus C over 2. We can implement rule number 2 in our drawing. In our drawing, we have this circle is blocked by the right triangle ABC. According to the new formula, the radius of this circle, that is R, must be equal to AB plus BC minus AC over 2. And repeat again, the radius of this circle that is blocked by the right triangle ABC, R must be equal to AB plus BC minus AC over 2. AB is 7, BC is 24, minus AC, that is 25 over 2. 7 plus 24 is 31, and 31 minus 25 is 6, and 6 over 2 is 3. So in conclusion, found out that the radius of this circle that is blocked by the right triangle ABC equals to 3 units in its length. Then we found out the radius of this circle that is blocked by the right triangle ADC. According to the new formula, the radius X of this circle must be equal to CD plus DA minus CA over 2. Repeat again, the radius X must be equal to CD plus DA minus CA over 2. CD is 7 plus DA is 24 minus CA, that is 25 over 2. 7 plus 24 is 31, and 31 minus 25 is 6, and 6 over 2 is 3. In conclusion, we found out that the radius of this circle X must be also equal to 3 units in its length. Then implemented here. Rule number 1. We define the point of tendency of tangent BC with this circle as M. We join points P and M together by straight line. The radius PM is drawn to point M, that is the point of tendency of tangent BC with this circle, and whenever radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MP. That is to say, this angle equals 90 degrees, and this angle also equals 90 degrees. We define the point of tendency of tangent AB with this circle as N, then we join points P and N together by straight line. Pn is the radius of this circle that is equal to 3 units. The radius Pn is drawn to point N, that is the point of tendency of tangent AB with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. So inside quadrilateral PN, PM, we have 1, 2 right angles, therefore the fourth angle must be equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral PN, BM, we have 4 right angles, therefore can relate to this quadrilateral PN, BM is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other, that is to say PN equals to BM. But PN is 3, therefore BM must be also equal to 3. According to the same rule, side PM of rectangle PN, BM must be equal to side NB, but PM is 3, therefore NB must be also equal to 3 units in its length. So actually found out that quadrilateral PN, BM is not a rectangle but a square. Why? Because all of its sides are equal to each other, inside here is equal to 3 units. If we repeat on the same process, on this circle that is blocked by the right triangle CDA, we get that quadrilateral KQGD, to rule number 1, this quadrilateral will be square, will be a square, the one side of this square, KQDG, will be also equal to 3 units in its length. Exactly, so those two squares, they are identical, each side of those two squares is equal to 3 units. So we have here 2 squares. We just have to implement rule number 1 in this drawing, and we get that this quadrilateral KQGD is a square. In the next step, we extended the radius GQ by a straight line until it touches side BC of the rectangle at point T. In this way, we created quadrilateral GDCT. In this quadrilateral GDCT, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. So quadrilateral DGTC has 4 right angles, therefore can relate to this quadrilateral DGTC as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, DG equals to TC, but DG is 3, therefore TC must be also equal to 3 units in its length. Likewise, according to the same rule, in rectangle GDTC, side GT equals to side DC. But DC equals to 7, therefore GT must be also equal to 7 units in its length. Here, GT equals to 7 units in its length. In the next step, we extended the radius NP of this circle that is equal to 3 units by a straight line until it touches side DC of the rectangle at point N. In this way, we created quadrilateral NBLC. In this quadrilateral NBLC, we have 1, in this quadrilateral NBCL, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside the big quadrilateral NLCB, we have 4 right angles. Therefore, the big quadrilateral NBCL is a rectangle because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NBCL, CL side LB equals to side LC, but LB is 3, therefore LC must be also equal to 3. Likewise, according to the sum rule, in this rectangle NLCB, side BC equals to side NL. But BC is 24, therefore NL must be also equal to 24 units in its length. This side NL of rectangle NLCB equals to 24 units in its length. So, inside the small quadrilateral ZLCT, we have 1, 2, 3 right angles. Therefore, the fourth angle, this angle must be also equal to 90 degrees. So inside this quadrilateral, the small quadrilateral ZLTC, we have 4 right angles, and therefore you can relate to this small quadrilateral ZLTC as a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, LC equals to ZT, but LC is 3, therefore ZT must be also equal to 3 units in its length. Likewise, in the same rectangle, side ZL must be equal to side TC. But TC is 3, therefore ZL must be also equal to 3 units in its length. So actually found out that quadrilateral ZLTC is not a rectangle but a square, because of the fact that all of its sides are equal to 3 units in their lengths. Okay, so we have here in total 1, 2, 3 identical squares. If each side of those 3 squares are equal to 3 units in its length. Here we extended the radius GQ by straight line, and the result is GT. When you extend the straight line by straight line, the result must be a straight line. So GT is one straight line. We have only found out that GT equals to 7 units in its length. So GT minus GQ minus ZT equals to the missing side QZ. Repeat again, QZ equals to GT minus GQ minus ZT. So QZ equals to GT, that is 7, minus GQ, that is 3, minus ZT, that is 3 also. So in total, QZ equals to 7 minus 3 minus 3, that is 1. So QZ, the missing 9 segment QZ equals to 1 unit in its length. And here, we just right now found out that NL equals to 24 units in its length. Here, NL equals to 24 units in its length. So NL minus NP minus ZL must be equal to the missing side PZ. Repeat again, PZ equals to NL minus NP minus ZL. So PZ in total equals to NL, that is 24, minus NP, that is 3, minus ZL, that is 3. So in total, PZ equals to 24 minus 3 minus 3 is 24 minus X. So PZ equals to 24 minus 6. PZ equals to 24 minus 3 minus 3. That is to say, PZ equals to 24 minus 6. So this side, PZ equals to 24 minus 6, that is 18. So in conclusion, we found out that PZ equals to 18 units in its length, while QZ equals to 1 unit in its length. So QGDK is a square, and GT is one straight line. If you focus on this side of the straight line GT, at point Q, here the sum of the angles must be equal to 90 degrees. So which angles we have on this side of the straight line GT at point Q? We have this angle that is equal to 90 degrees, therefore the missing angle must be equal to 90 degrees also, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. According to the same rule, if we focus on the straight line DC at point K, the sum of the angles must be equal to 180 degrees. So which angles we have on this side of the straight line DC at point K? We have this angle that is equal to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees, according to the rule that I mentioned. So those two angles are both equal to 90 degrees. Then we focused on this side of the straight line DC point L. This ZLCT is a square, therefore this angle equals to 90 degrees. And DC is one side of the rectangle, therefore it is absolutely a straight line. So at this side of the straight line DC at point L, the sum of the angles must be equal to 180 degrees. Therefore the missing angle must be equal to 90 degrees. So inside quadrilateral QKLZ we have 1, 2, 3 angles, therefore this fourth angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So this angle equals to 90 degrees. So if we focus on the upper side of the straight line NL at point Z, here the sum of the angles must be also equal to 180 degrees according to the rule that I mentioned. So which angles we have at the upper side of NL at point Z? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle must be equal to 90 degrees. So if this angle equals to 90 degrees, it means that the green triangle PQZ is the right triangle. So I copied the right green triangle PQZ in a new page and we implemented the Pythagoras theorem on this right triangle, triangle PQZ. Side PZ equals to 8 units in itself, side QZ equals to 1 unit in itself, and this angle is the right angle according to rule number 2 that the sum of the angles on one side of a straight line is equal to 180 degrees. By PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, in this right triangle QPZ, QP squared, that is the square of the hypotenuse, equals to QZ square plus PZ square. So QP squared, that is the square of the hypotenuse, must equal to QZ square. QZ is 1, therefore QZ square is 1 squared, that is 1, plus PZ square. PZ is 18, therefore PZ square is 18 squared, that is 324. In conclusion, we found out that QP square equals to 324 plus 1, that is 325. We took out of this equation and found out that QP equals to the square root of 325. But 325 is 25 times 13. We can take 25 out of the root. The square root of 25 is 5. So inside the root we left only with 13. In conclusion, we found out that the distance QP between the centers of those two circles, it is equal to either 5 times square root of 13 units, or in terms of numbers, QP equals to 18.03 units. A little bit greater than 18 units. So QP equals to either 5 times square root of 13 units, or in terms of numbers, QP equals to 18.03 units. Okay, thank you very much.